a bit late, but yeah, so we'll move on to the next speaker. Um, right, so next we have Professor Bruno Fernandes. He is an associate professor at the University of Pernambuco, and he focuses on deep learning, reinforcement learning, and computer vision. His topic for today is reinforcement learning for robot control and interaction. So unfortunately, Professor Bruno could not make it today, but he did manage to send in a video, which I'll be playing here now.
Well, Tom, in fact, I'm online, but I would prefer if you show the video anyway.
Okay. Good to know you're here. All right, I'm just playing the video. Yeah.
Hello, everybody. My name is Bruno Fernandes, and in this presentation, I'm going to show some works regarding reinforcement learning that are being conducted in the Universidade de Pernambuco at Brazil. I'm going to briefly describe 6 projects from different master and PhD students, and then me and the students will be available to try to answer some of your questions. The first work, titled A Deep Reinforcement Learning Approach on Camera Control for Intelligent Active Object Tracking, is being conducted by Davi Barrientos and Professor Sérgio Murilo with me, Bruno Fernandes. Much of the existing work regarding object tracking is based on passive tracker, where it's assumed that the object of interest is always in the image scene, making it not suitable for most real-world applications. For such applications, it's required active tracking, which unifies 2 subtasks, object tracking and camera control. Furthermore, some real-world applications require an intelligent initial annotation, as some events cannot be manually pointed by a human, especially those fast enough to not be detected by the human eye. This project proposes then the use of deep reinforcement learning, specifically Q-learning, to create an active object tracking controller capable of optimal control strategy in a real-world application by learning from the environment. Deep learning will be used to define a suitable real-world function to aid the learning process in digital image processing. Will be used to define a policy capable of detecting interesting events and providing an automatic annotation for object tracking. Regarding the evaluation, the results will be evaluated over the system's capability to actively track objects and to automatically provide initial annotation. This can be quantified using the cumulative reward alongside the number of steps. An analysis will be done to determine 3 things. First, the asymptotic slope to determine how good the policy is after the algorithm has stabilized. Then, the minimum of the curve to verify how much reward must be sacrificed before the system starts to improve. And finally, the zero crossing, as it shows how long it takes until the algorithm has recouped its cost of learning. The second work is titled Robust Approach to Continuous Interactive Reinforcement Learning and is being conducted by Christian Milan with the participation also of the Professor Francisco Cruz. We first highlight in this work that interactive robust reinforcement learning addresses 3 simultaneous problems. Those problems are the problem of representing a complex space. In many reinforcement learning implementations, the space of states and actions is usually considered a discrete domain. And the second problem is about the learning time of autonomous agents. To leave an agent to find an optimal policy requires excessive time, mainly due to a complex and large state action space. Finally, the influence of external disturbances in the environment. It's not guaranteed that the environment is kept in constant condition avoiding some external noise input. Two approaches are then proposed for these three problems. First, the continuous interactive robust reinforcement learning is an approach to integrate external device while learning an agent reinforcement learning. The main idea is to consider the policy as the combination of an external device policy, also known as feedback policy, and the agent policy in continuous spaces. The second approach is the interactive robust reinforcement learning that considers the interactive approach in continuous space, but considering that the environment is dynamic. I mean, the environment is modified by an external disturbance. The main idea is to filter the disturbance from a disturbed real world. We implement a simulated robot arm for the task of organizing different objects in order to evaluate the proposal. The objective is to classify 6 geometric figures with different shapes and colors into 2 design regions over a table. Our results shows that interactive robust reinforcement learning agent in dynamic environments obtains a higher performance than a robust reinforcement learning agent. A robust agent acting in a non-dynamic environment performs poorly because internally the real-world filter is moving in states. In the third work, also by Christian Milan and with the collaboration of Professor Francisco Cruz, it's titled Teaching Proxemics Behavior to Robots Using Reinforcement Learning. And it seeks to improve the learning of proxemic behavior in reinforcement learning agents with humans or other cognitive agents. Proxemics is a branch of nonverbal communication that studies the use of personal space. Due to the increase in research in human-robots interaction and the implementation of robots in social environments, an optimal interaction between artificial agents and humans is necessary. So we can give these 3 reasons for why teaching proxemics to robots. First, in recent years, human-machine or human-robot interaction has taken root in the scientific community. Then, the humanization of machines is an expected event given technological advance and the human nature. And finally, the need for optimal interaction is necessary, both on the machine and the person. However, currently, several works that implement the proxemic theory consider fixed personal space independent of other nonverbal aspects. But physical and psychological factors also influence to personal space. In this problem, the goal is to train an agent or a robot to approach a person using reinforcement learning. First, the robot must identify the social aspects of the environment and propose the best way to approach the person without disturbing him. Furthermore, during the approach process, the agent must identify which is the region of space and the minimum distance where he can interact. Then the robot must estimate the optimal distance to interact with the humans, and it is the main objective of this work. With this investigation, it's expected that the agent approaches in the best way to a person, avoiding disturbing him. It's intended to measure the impact of each social aspect on the conformity of the person and proxemic behavior. In addition, the agent is expected to estimate an optimal distance and the region where he can carry out the interaction process. The fourth work is titled Empathic Emotion Planning Using Deep Q Learning and is being conducted by Agostinho Freire Jr., considering that the social interactions in closed space are the target to be avoided in robot path planning. In path planning problems, the main problem concerns for solutions that are able to generate the shortest path and deviate from the objectives that arise along the way. However, when you talk about closed environments with social interaction, taking into account only these two factors is not enough. It's necessary that the routes generated by the algorithm do not generate any negative impact on the people present in the place. To solve this problem, we created 5 scenarios simulating common situations such as conversations, movement, groups. Furthermore, a deep Q-learning algorithm was used to generate the paths to be applied by a robot. The results obtained show that even in deadlock situations, the algorithm was able to minimize negative impacts on those present in the environment, choosing the least negative actions within the context. Finally, as said, the algorithm was able to positively converge decision-making, being able to achieve the established objectives and criteria, thus reducing the impacts that could be generated along the trajectory. In the fifth work, reinforcement learning for unmanned aerial vehicle continuous control in fire image response, that is being conducted by Angel Ayala with the participation also of Professor Francisco Cruz. It's proposed to develop an agent to solve an object navigation problem. Given the scenario of fire, the agent must be able to achieve a searchlight flight behavior to locate an object of interest. Additionally, the agent needs to recognize the fire presence to identify the object of interest. To do so, a wildfire scenario was developed in Webbot's robot simulator. Here, we got an example of the simulation scene with the drone and the fire accident. In this early stage, the Markov decision problem contains, first, as stated, the RGB image from the drone's camera, cropped square and resized to 84 times 84 pixels. Second, the actions are considered in continuous space, angles, and the altitude of the drone. Third, the transition function is delegated to the simulation software, which contains the necessary to replicate the real-world dynamics, with the exception of the fire, which is a fire flame video with no heat transfer dynamics. Finally, the present, a dense real-world function, which depends directly on the distance between the drone and fire position. Here, we got our preliminary results, where the drone is able to fly inside a delimited zone in a search-like behavior. Our future work aims to introduce representation learning to improve the recognition of the target object, or more specific, the fire. It's expected to obtain a simple time-efficient algorithm capable to run in embedded devices. The final scope for this work is to develop a real-world fire response drone system. Finally, the last work is titled Vision-Based Robotic Manipulator Control and is being conducted by the PhD candidate George Azevedo. In this work, robotic manipulation using visual feedback is investigated. It is an important topic for many industrial applications that use robot manipulators, such as fruit harvesting, welding, equipment inspection, and grasp in general, as shown in the video. The robot's manipulators are composed by actuators and sensors, and to control the system, it's necessary to model its dynamic, based on system states obtained from physical sensors. In this research, we investigate how the manipulator can learn to act without the use of physical sensors data, only using visual feedback to grasp objects. The system is training using reinforcement learning during robotic manipulation. This approach will be tested and evaluated during grasp and positioning tests. First, simulated tests will be conducted, then we perform some experiment positioning tests. It's important to note that the learning ability with few modeling parameters is a key point in this research. Finally, we are going to evaluate the framework adaptability to different manipulators model. The parameter to evaluate the framework is the rate of successful tasks and the number of attempts to achieve this number. Thank you for your attention, and that's all about the work with reinforcement learning that we are developing at the Universidade de Pernambuco under my supervision with the collaboration of other researchers such as Professor Francisco Cruz. Thank you very much.
All right. Thanks a lot, Professor Fernandez. Do we have any questions? I just want to ask, so with regards to this proxemic behavior, I imagine that, you could have humans could, their mood could change from day to day, hour to hour. And based on that, they may not want like the agent very close to them, or they may want the agent far away, for example. Is this one of the angles that you're looking at in this problem?
Yes, in fact, this work is being conducted by Christian. He's online also. I think he can complement my answer. But this is the thing. We want the best way of the robot to approach a person. So he's trying reinforcement learning as a solution because, as you know, we have some cultural aspects regarding the distance we should keep from one to another. Here in Brazil, for example, we usually talk to each other in a much more closer way than in Europe, for example. But after the pandemics, people is a little bit scared about being too close to another person. So it might also make some have some effect on the person's behavior. So if you want the robot to not invade the personal space, not to be inconvenient during his actions, so we should take this in consideration. And the most, sorry, it's my kid. The robot should be should be capable of adapting itself to the situation. Christian, do you want to say something else?
The audio is very unclear, Christian.
Can you hear me?
It's very unclear. Okay, that's fine, I think. Another thing that I was wondering is you talk about the negative social impacts that are considered for that path planning problem. I was wondering, like, what kind of negative impacts you're referring to?
Yes, this is the I would say like two works they work together. This path planning and the proxemics, because the path planning is about going from point A to point B and without interfering in, for example, a conversation of two persons. Obviously, we could be talking about a very small robot of 1 centimeter, or maybe it's a 2-meter robot, or it's a car, or something like this. And in the proxemics, it's about how to approach someone. They have a interconnection between both projects. So the path planning, the negative interference that a robot might cause is supposedly we have a conversation now in a physical way, not in this virtual way, and then a robot just passed by in front of us. Or imagine if a person, if we are talking in half a meter and a person passed in the middle of us. So it's a little bit strange to disturb the conversation. And supposedly we are in a hospital and I'm a doctor, you're a patient, you are very sick, and someone keeps going on and back in front of us. So it's annoying. And we don't want a robot to have this kind of behavior. Agostinho is the student responsible for this work. Agostinho, do you want to complement with something?
Hello. No, I think it's basically it. When we are calculating the path planning, the robot path planning, we just don't want to interfere in people normal actions, you know, such as conversations, movement, things like that. Basically it.
Right. All right. Yeah, thanks a lot. Not sure if we have any questions in the chat yet. Yeah, seems like we don't. But it's okay. I think we are right on time for the next talk as well. So thank you, Professor Fernandes, for that great presentation and for really kind of condensing this, I think, 6 works into one presentation. It's not very easy. And thanks a lot for accepting our invitation as well.
Thank you,
So
Tom.
with that,
Thank
yeah,
you very
thanks.
much.